Hi, today we'll be discussing about AA fleet quality. What are the challenges? What are the solution space we are looking at debug, diagnostics and RAS enhancements. And I'll cover what are the contributions we are making in this space and also about diagnostics. Jicksen will be discussing about debug and Taniya will be discussing about RAS. Someone asked a question, hey, there are 3 work streams in GPU work stream. There is a RAS, did we drop it or not? Because of how we combine the talks, because of the time limits, there is a split of GPU work stream and merging of CPU work stream, right? In this talk, we'll be talking about GPU work stream contributions and CPU work stream related to debug, diagnostic and RAS. And first thing, I think previous talk provided what are the benefits for new members. I'll just give a quick summary, right? As a hyperscaler, right, we need to integrate multiple silicon from different vendors. Either it comes from GPUs, like their first party own accelerators, right? You have a CPU, then there is a network card. There are many devices, right? And for this, we want to seamlessly integrate into each hyperscaler environment. And previously we used to work, each hyperscaler used to work with individual silicon vendors. It's a lot of time consuming and the requirements varies and the product intercepts, you need to negotiate separately and all. Lot of work has been done on integrating, rather like innovating what we can do on top of it, right? Once we standardize, adopt this for hyperscalers, it will provide opportunity to innovate on top of the general work we do for integration. For example, at a scale data we have, we can do predictions, we can get insights, give feedback to next product. There are many things we can focus on than standard integration, right? Suppliers also get the similar benefit. They're all talking to the big hyperscalers and all the minimum requirements, which is required, high prioritized requirements, they can support. On top of that, silicon vendors also can innovate on other areas those are the main things, right? Before I go to the fleet quality challenges, I just want to pick up a scenario, right? Assume you are doing a large language model training, right? The training workloads require thousands of GPUs. All these GPUs work synchronously, okay, to get a model trained. Each training takes weeks to months, okay? Think through that scenario, right? When you have thousands of GPUs, right, each GPU is trained on small set of data, okay? The reason I'm giving you the context, you understand the difficulty of what we're trying to solve, right? Each GPU trains on the small data set, but all these GPUs need to be synchronized for their output results to make a progress, right? People use this PyTorch and all these frameworks to synchronize the outputs, okay? And at that scale, how does it impact hardware failures, right? You have seen general purpose compute, right? The blast radius of general purpose compute, whether if you see a memory error, CPU error, right? The blast radius of that error either belongs to a particular VM or a node level. Whereas on GPU SKUs, with the training especially, the blast radius is huge because all the each GPU results need to be synchronized to make a forward progress, right? Each node failure can have very big blast radius. And I know there are some techniques like checkpointing and all, those are very costly. Each checkpointing takes time, it increases the total overall training time for it, right? That's why we want to focus on improving the availability features, how do we reduce the blast radius, how do we get better telemetry to improve the RAS features, right? Next thing about, like many of you know, getting a GPU capacity is in these days, like there's a lot of competition, and also they're very accelerates, very costly, right? Whatever you acquired the capacity, you want to keep all of them into the fleet operational. Those are all working for workloads, not there for repairs, waiting for root cause, what do we do? Whatever the RAS telemetry it provides, on top of that, you want to do diagnostic improvements, okay, standardize them. That is the second pain point, that's where we focus on the diagnostics. And the next one is about issue root cause, right? In general purpose compute, you have a single node. Now compute has become a rack level, cluster level, right? If you see like general rack level, you have compute nodes, lot of interconnects, okay? That rack level, there will be a lot of more failures, okay, than you see in a single node, okay? Issue root cause becomes very critical. The SLA to root cause those issues becomes very critical. You need to have like additional crash dumps, debug dumps, and that's where we focus on the debug features. The debugging has two levels, right? One you do in the node lab level. The same features may not work at a hyperscale level, like the security requirements, how do we enable those features, all different. That is the delta work, right? In overall, like it requires to support diversity of silicon, you need standardization. OCP is the like platform we are using to interconnect, right? As I mentioned, like there are two work streams. One is GPU management work stream, okay, and other one is CPU management. Supposed to be separate talks, but that's why you see the contributors are a little different, okay? As you see on GPU management work stream, we started this like 2+ years back, okay? This is the first effort to standardize GPU RAS requirements. Last year, we published a 1.0 version, and now we are contributing 1.7. It's under steering committee review, and it will be done by this month end, okay? Their contributors are AMD, Google, Meta, Microsoft, NVIDIA. Taniya is going to little bit deep dive into the RAS, what are the delta features we have, right? On the CPU side, we started this work stream like a year back, right? We have like all the CPU vendors, AMD, ARM, Intel, and Google, Meta, Microsoft are the hyperscalers. This is a little bit recent work stream, like, but as you see the progress, we released a 0.5 version, which focused on the debug, okay? There, especially CPU debug features across x86 and ARM, there is a lot of variances and all we want to standardize, okay? And go a lot more depth into type of debug features, okay? And we published a 0.7 version, more focus on the 0.7 version. I'll share some details on the what are the diagnostic improvements we added into the 0.7 version. Like you saw the scenario, right? When you see the rack scale, like the number of devices, suppliers which goes into the rack scale, either accelerator, memory vendors, network, there is many hardware types, right? Each vendor provides a diagnostics tools. Even some vendors have both GPU, CPU, and other memory tools. What we observed is like each vendor across the vendors, there is a lot of variance how they release the tools, and then as a hyperscaler, we need to integrate and we need to test it, and we need to work with them individually and how to understand. That is one of the biggest pain point. What kind of physical interfaces they leverage, what APIs they provide, especially on the Microsoft mostly uses Windows. Now we are moving to a lot of work on Linux, we want to standardize on Linux. all the dependencies vendors can focus, like take a particular Linux kernel version. I know Linux also multiple distributions, but as you focus on the kernel and test those, okay, and that's where we're focusing on, like how do we package all the things into one thing, right? We'll talk a little more details about the diagnostic recipe. Like generally when you provide the diagnostics, generally like you provide a documentation, hey, run this tool this way. It's all manual techniques, and also sometimes like when we see the fleet issue, we reach out to the vendors, they say, oh, run this way. This is the different recipe you need to do. Maybe the optimized for link errors and all that, right? But like that is the other problem we have. And last one is about repair actions, is mostly focused, I would say, is on what are the tool errors, what are the silicon is observing, rather thinking about a data center technician, right? With the complexity, like you see liquid cooling and all that, how do we replace the, one part is very hard now with the complexity, right? You need to think through repair actions in the point of service technician or like firmware updates, okay? You need to show the results into action oriented, not on the what you're observing, okay? And for this, like we spent some time, okay? Even though it's part of CPU, like we made these requirements in generic, which can be applied for CPUs, accelerators, PCI devices, okay? Like we used that platform as a CPU workstream to publish the spec, but we are going to leverage this across all other components, right? And the second thing is about the tools requirement, right? We want same tools to work in manufacturing, development phase, and production. Like that is the other problem we observed. Like, hey, you get some tools or recipes are different, and we want to standardize across the node life cycle. And if you see in this picture, right, we put in 5 steps are the main pain points. One is when you develop the tools, other one is when you test it, the tools. Third is like integration, when you integrate into hyperscaler or enterprise environment, right? And when you execute it, okay, what problems we face, then when you're taking actions. These are the major areas for the tools. Like we're providing the requirements across like what kind of environment, like all hyperscalers are recommending suppliers to develop the tools, and dependencies, let's say like you need some special additional code through driver form or something, like put those into package, right? And the second advantage is like hyperscalers used to test this one. Now with the standardization, because all are saying similar things, a lot of work suppliers can go and test that against those requirements, then we can easily integrate. And we can leverage, we don't need to duplicate that effort, testing by supplier, testing by hyperscaler, because of standardization, right? They can share the results, we do minimum test, right? That will help us save on resources. Next thing is integration becomes easy, and on execution, especially when you see errors with the link problems and all, like whenever we reach out to different suppliers, so, oh, link, you need to run different tool. The recipe is different. Go change from somewhere, firmware settings. Like there is a lot of knowledge is shared across meetings, requirements. That's why like Rajat provided a talk this morning. How do we do recipe generation by tool, right? There's an open source contribution coming up, like you can use that tool to generate the recipes, optimize it, okay? Next thing about action, we want to focus on the what can be done as a repair than looking at a silicon point of view. Those silicon point of view results, you can get it from like say RAS telemetry, what logs and all, right? There is a lot of requirements specified in hardware fault management workstream. Those are the things. I'll give it to Jicksen to cover debug.
From a debug perspective, we have an industry state situation where we have tool fragmentation, as Rama was talking about. The tool sets that comes from each supplier is different, and the solutions that they give are also very custom because they allow us to kind of debug in a certain way, and there are gaps in features between generations of a given supplier. So this is where we are today. Where we would like to go is where we would like to have a general debug workflow where we are monitoring the failures happen, and then in cases where we need additional information, we then configure and collect further information. So where we really would like to be is in the collection stand, where failures happen, we are collecting the logs, and then we act on them. So the common collection mechanism that we would like to hit would be crash dumps, where when a CPU or a machine fails, we have the crash dump. The crash dump gives us very clear action signals, and then we act on them. Now, that's going to be the predominant part of how we work, but in rare cases where a small subset of the failures, we would need additional information so that we could debug further. Now, normally this happens during NPI phase where you're in the development cycle, but many a times after your production, you do have to go into some kind of debug cycle. So we would like to have that capability also available. And this debug cycle mainly requires additional information, which crash dumps normally don't provide, which could be extended register dumps or trace dumps. It could also be a state machine of how the machine is, so state dumps or scan dumps. We'll talk more into how these differ. So in a crash dump scenario, what you have is a fatal error that happens in a GPU or a CPU or a switch link, etc. And this causes the crash. So that becomes the trigger event. And based on the trigger event, you then go collect the time of the failure. And based on the failure that you see, you then ascertain whether it is a normal failure or it's a failure that kind of has to have an action upon. And in some cases, you probably need an analysis tool. So some of them are pretty straightforward. Hey, if I see this dump, if I see this signal, this is what I need to do. But in many cases, you will need a parser or an analyzer, as we call them, where the crash dump is then analyzed by the supplier-provided analysis tool, which then allows us to take the RAS action and kind of indicates what should be the next step that we should do. And in certain cases, we would need assistance from the vendor when the crash dump analysis probably needs further information, but that's kind of the more detailed part of it. So this whole flow happens automatically, and it is a collection that happens on fatal failures, and it happens on demand. Now, the requirements are, obviously, we don't have any customer data here. It has to be persistent across a reset because a crash dump does cause the machine to reset. And then you want to make sure that this is usable across not just the current product, but it's kind of standardized so you can use it across the development phase and in production and across multiple generations. CPR is a format that we are all familiar with through the OCP efforts from the fault management workstream, and that's what we want to align with. From a debug perspective, now we are kind of going into that exceptional failure mode, right? Where this is a smaller subset of failures that we see, where we want to collect the additional information. This would require configuring or unlocking the system in some cases, glass break as we call it. This happens on demand, and the requirements for that would be having scan dumps, trace dumps, or additional state machine dumps taken. We would like this would be in the CPR format, and it would use the same software interface as the crash dump. So between these two, the functional mode would be the same. It's just that there is additional data that is provided, which allows us to do the debug. And we would like to have this in production, so it makes debug at scale pretty useful and easier to consume. With this, I'll let Taniya talk about the GPU RAS part.
Hello, everyone. I'm Taniya Siddiqua, GPU RAS architect from AMD. So my colleagues here talked about standardization efforts on diagnostics and debug, crash and debug dump. I'm going to focus on the GPU RAS requirement standardization. CPU RAS has been covered in other sections, so I'm not going to focus on that part. It will be just the GPU side of things. So from GPU RAS point of view, we have published our version 1.0 spec last year, September. The focus has been on RAS metrics and what should be the targets around them. So essentially, the main point here is, given the AI era, we have now new kinds of workloads. We have training, we have inferencing. They can be run concurrently on multiple GPUs. So things are different. So the traditional RAS metrics would not just be applicable as is in this new AI domain. So what we looked at is, with the concurrency thing in mind, how do we tweak the RAS metrics and what would be the more applicable ones? We also looked at fault handling requirements for system, PCIe, GPU, and so on. Since then, we have been meeting every Friday, talking about how can we make further progress, and the existing requirements that we have come up with in version 1.0. We have discussed further and made some tweaks and updates based on the feedbacks. We also have looked at expanded system and component level crash and debug dump that Jicksen just covered. And lastly, we have looked at the error analysis tool requirement, which is what I'm going to talk mostly about. All right, so before I head into that, let me just quickly touch on what is our next version scope. So we are going to look at blast radius reduction. Rama has talked about how in the training and inferencing world, how the impact can be much bigger and how we want to be able to use our cluster more efficiently. So we will focus on that. We will also look at confidential compute and RAS, what should be the requirements, keeping both of them in mind. And last but not least, we want alignments with other hardware fault management domains, for example, RAS API. So we had a talk this morning on RAS API, what should be the RAS interface, how the error collection should look like, how the actions should be looking like in the fleet. We want those to be part of the GPU RAS workstream as well, so that they are working together seamlessly. All right, so with that, let's look into the error analysis tool requirement. So OCP is all about standardization. It should be helpful for both vendors as well as the CSPs. So how does the error analysis tool would help us, right? So here in this diagram, we are just showing a typical error analysis infrastructure. The tool, error analysis tool itself, the green box in this diagram, that should come from the vendor. So the idea is we want all the error information routed to the vendor, and vendor would output some information. So the standardization part here would, we are looking at it from two different points. What is the input going into the tool, and what's the output coming out of the tool, and how can we standardize those, right? So CPER, we have been talking about CPER for a long time. That's a standard defined by UFI, CPER Common Platform Error Records. So as you know, in the CSP fleet, we can have a lot of different vendors, and each vendor would have their own error logging infrastructure. So we want all those error information captured in CPER format. The CPER error record would be routed into the vendor 2. So to be able to route those information to the right vendor tool, we will parse the error information that will be routed to the right vendor. That's where the green box here. Now, the other point here is, as we have been saying, debug dump, crash dump, all those should be in CPER format, right? So here, what we want is all kinds of errors, correctable, non-fatal, fatal, crash, debug, everything should be in CPER format, and everything should be going through the same plumbing, same software interface. In some cases, to do the root cause analysis, history is helpful. And that's where if you see the other blue box there, previous CPERs, so that's essentially the history of from that vendor. You would want to feed into the error analysis tool. That then the error analysis tool will take the current CPER as well as the history, and then would do an analysis and come up with some recommendations. So what sort of recommendations we are looking for? It could be simple flu replacement. It could be, hey, you need a firmware update. It could be that, hey, this is a debug dump. Debug dump analysis is supposed to be done by the vendor, so contact your vendor so that the information is being sent to the vendor. Now, when the tool has done the analysis, how the output is supposed to look like. So the first piece is the JSON output. JSON output is supposed to be human readable as well as machine parsable, so that the actions the CSPs are able to take the right action based on the output. So that's what it's showing on the right-hand side. Further analysis, dashboarding, CSPs can do whatnot. The other output that's showing in the bottom, CPADs, common platform action descriptors. So this is another output that has been discussed in hardware fault management forum. In this morning's talk also, they touched a little bit on this. So the CPADs, it will go through the CSP policies. The idea is it can directly go to the OS or to the BMC to take the action, or it can also say manual intervention or send to the vendor and whatnot. For the CPAD route, we are relying on the hardware fault management workstream. So as I said, our next version, our focus will be combining RAS API, how it will all look like. So in the next version, we will have the complete picture here. So with that, call to action. So as Rama mentioned, for GPU RAS spec, we have version 1.7. For the CPU, it's 0.7. Please take a look at it. Please provide feedback. Any questions and any updates are welcome. And welcome to join our group. We have the mailing list and the group discussion. So with that, we are ready for any question.
All right, let's thank our speakers first. We probably have time for one question. So if you have a question, go to the mic and ask.
We are self-explanatory. No question.
Hey, thanks for the wonderful update. My question is on GPUs, right? And especially the last year or so, we have seen the GPUs have grown out of the box into more into a scale-up networking, right? Where it's a rack level or multiple racks where the GPUs are connected over a coherent network, right? Either be ESN or what are the proprietary protocols. I think the single biggest issues that we see is rack level failures here, right, on the scale-up networking, right? I would like to see how moving away from a node, right, into more of a rack level RAS, right? How does this OCP forum look into it?
Yeah, like there are a few discussions happened. That's where like we're talking about like a cluster level. How do we like blast radius? And that is the next version of the thing. And the current version like talks about link errors. For example, when you go at scaling at the rack level, either you use different proprietary protocols or something. Those things are covered. But next version, like you called out, like that is a very first thing we want to tackle that.
Yeah, that's the single biggest pain point.
Yes,
today, right?
yes,
so
yes.
I think it'll be good to see more standardized.
Prioritize on that. Yeah. Thank you. Yeah,
Thanks.
we'll prioritize that and release it. Maybe 1.9. Don't wait for 2.0. Yeah.
Thank you.
I think we don't have time. So questions, if you can take it offline. Once again, thanks.
Yeah. Thank you.